While a language model is answering you, it produces a list of 128 numbers for every word it has already read, and it has to keep every one of those lists, because before it writes each new word, it reads all of them again. Written the ordinary way, one list costs 256 bytes, and on a large model in a long conversation, the whole collection reaches 40 gigabytes that has to be pulled out of memory once for every word produced. This video is about keeping the same list in 48 bytes instead of 256, which means allowing each of those 128 numbers only 8 possible values, and about what you give up by doing that. The first thing you will see is the obvious way to do it, which is to look at the numbers you were handed and fit the 8 values to the range they happen to occupy, and you will see why that fails, because the range has to be stored alongside every small block of numbers, and storing it hands back about a third of everything the compression just saved. The way out is to stop adjusting the 8 values to suit the numbers and instead spin the whole list of numbers at random before storing it, and you will see why spinning something at random makes what comes out more predictable rather than less predictable enough that the 8 values can be fixed in advance before a single number has been looked at. You will find that the 8 values which were published decades ago for an unrelated problem, that the spin is the entire reason you're allowed to reach for them, and that what you get in return is a guarantee, meaning the error comes out the same size, whoever handed you the list, including somebody who picked it deliberately to break the method. Then the video argues against itself, because a method can be the best available at rebuilding a list of numbers and still be wrong for what the model actually does with them, which is not to rebuild them, but to multiply them. And the correction that repairs this works exactly, costs 1 extra piece of information per number, and was removed by every team that shipped this method in real software for a reason you will see is right. At the end, you will see what all of it actually buys, which is room rather than speed, and you will see the cases where it makes the model slower instead of faster. Every figure in this video was either measured on a running model or taken from the paper. You will see which one it is at the moment it appears, and nothing has been rounded in the direction that flatters the method. Here's a vector. It has 128 components, just a list of numbers, 1 bar each, stored the usual way in half precision. Each of those numbers takes 2 bytes. So the whole vector costs 256 bytes. I want it much smaller. 3 bits per component. Not 3 bits for the whole vector, 3 bits for each one of the 128 numbers. That adds up to 384 bits, which is 48 bytes. So how well can you describe a direction in 128 dimensions using 48 bytes? 3 bits gives you 8 patterns. So there are exactly 8 numbers you're allowed to write down, and each of the 128 components has to turn into one of those 8. Nothing else is allowed. Which means the only real choice is where to put those 8 values. The numbers run from about -1 to about +1, so spread the 8 evenly across that range. 8 tick marks, 0.284 apart. Every component then moves to the nearest one. Before I run it, take a guess. How many of these 128 numbers survive? 1. The largest component is 0.9942, and it lands on the top tick. Every other component is smaller than half the gap between ticks, so every other component rounds to 0. All 127 of them. The squared error is 0.0989, about a tenth of the vector's squared length. That is bad, and it is not the interesting part. The interesting part is what you actually sent. This vector points along axis 1. That is the whole message. You can put a price on that message, naming one axis out of 128, and saying whether it is plus or minus takes 8 bits. 8. You spent 384. 98% of that budget described nothing at all. That is not because I picked an unfriendly vector to make a point. Vectors shaped like this one come out of real transformers, and they come out in huge numbers. When a transformer reads text, every token it has already seen leaves 2 vectors behind. There is a key and a value in every attention head of every layer. To work out the next token, the model takes a new query and compares it against the key of every token it has seen so far. Every single one. It could work those keys out again every time, but that means pushing the whole history back through the network for every new word. The cost of doing that grows with the square of the length, so they are kept instead in a store called the KV cache. One key vector is 256 bytes. There are 8 key heads in a layer, a value alongside every key, 80 layers stacked on top of each other, and 128,000 tokens of context. Multiply that out for a 70 billion parameter model, and the cache is 40 gigabytes. And it is not 40 gigabytes sitting quietly somewhere. Attention has to read all of it to make a single token. So the whole thing gets pulled out of memory and then pulled again for the next token and again for the one after that. That is why anyone would accept 3 bits per component. Throwing away 98% of your budget is just an oddity when the budget is 48 bytes. At 40 gigabytes, read back thousands of times, it is the whole problem. So make the grid smarter. That is the obvious fix, and it is what the industry actually does. One grid had to cover all 128 components at once. So stop asking it to. Cut the vector into blocks of 32 and give every block its own grid matched to its own range. The block holding the spike still gets a coarse grid because it still has to reach 0.9942. The other 3 hold nothing but small numbers, so their grids can be fine enough to tell them apart. And it works. The small components stop rounding to 0. Now the bill. Every block needs 2 numbers of its own before anyone can decode it, where its grid starts and how far apart its levels sit. Both are stored in full precision right next to the data. 2 16-bit numbers for every 32 values. That is 1 extra bit on every value. You asked for 3 bits per component. You're storing 4, a third more than you promised. You might get around that bill with bigger blocks. Take the block up to 128 and the extra cost falls to 1/4 of a bit. But a block of 128 is the whole vector. The spike comes back and the small components die again. Block size is a dial between 2 failures. Turn it one way and the metadata eats your budget. Turn it the other and the grid can no longer tell any 2 numbers apart. No setting gives you both. There is a second door, and it is the one most quantization methods walk through. Instead of measuring the data as it arrives, build the codebook offline from a sample of typical vectors. Do that and you carry no metadata at all. That door is closed here. A KV cache does not exist until the model runs. Its vectors are built by the model as it goes, and they depend on whatever text you feed it. There is no sample to look at. Both doors are shut. So the code has to do all of this at once. One codebook, fixed offline before seeing anything. Good on every vector any model produces, including the worst one you could be handed. And no per block constants. That should sound impossible. Well, it sounds impossible because of an assumption sitting under everything so far, one that has never been said out loud. Every attempt so far moved the grid to fit the vector. That treats the vector as fixed, as something you were handed and simply have to describe. But nothing forces that you do not have to move the grid. You can move the vector. So before you quantize anything at all, multiply the vector by a random rotation. A rotation in 128 dimensions is exactly what it sounds like. You turn the whole space, and everything in it turns with it. Nothing stretches and nothing shrinks. In coordinates, it is a matrix, and a random one is just a random new set of directions for the axes. The spike is gone. The largest component was 0.9942. Now it is about 0.2554. Ask how many components are actually carrying the length. If the length were shared equally among some number of them and all the rest were 0, the count would come out at exactly that number. Before the rotation, it is 1.02, which is a long-winded way of saying 1. After the rotation, it is 43.5 out of 128. You have just scrambled the data. Have you broken it? No, a rotation keeps every length and every angle exactly, which together means it keeps every dot product. Rotate 2 vectors by the same matrix and their dot product does not change. Not roughly. Exactly. And a dot product is the only thing attention ever asks for. It never looks at a key one coordinate at a time. So rotating every key and every query by the same matrix is completely invisible to it. Distances are kept too. However far the reconstruction ends up from the original in the rotated frame, it is exactly that far once you rotate everything back. So you can measure the damage in whichever frame is easier. And there's only one matrix, not one per vector. That would be silly because you would have to store it, and a 128 by 128 matrix is far larger than the vector it was meant to compress. This one is drawn once from a single random seed. When the model loads, every key and every value in every head of every layer goes through it. To get it back later, all you keep is the seed. So that is the intuition. Spinning the vector spreads it out, and spreading it out has to help. But intuition is not what makes this work, and the spike got smaller is not a codebook. The real statement is stronger and stranger. It is the thing that lets you choose the 8 levels before you have seen a single vector. Choosing 8 levels before you have seen a vector means knowing ahead of time what the components of a rotated vector look like, which cannot be done because the vector has not arrived yet. Our vector has length 1, so it lives on the surface of a sphere in 128 dimensions. Now apply a rotation picked completely at random. That rotation never looked at where our vector was pointing. So what you end up with is a point spread evenly over the whole sphere. That is stronger than it sounds. Spiked, flat, adversarial, it does not matter what the vector was. Once you rotate it, all that survives is an evenly random point on a sphere. So stop asking questions about the vector. Every question you have is now a question about the sphere. Take one coordinate, any one of the 128, they are all the same by symmetry. Call its value z. How likely is z to be small, and how likely is it to be large? Because the point is spread evenly, the chance that z lands in a narrow band of heights is just the share of the sphere's surface sitting at those heights. So the whole problem is this. How much surface is there at height z? Slice the sphere with a flat plane at height z, where the plane meets the surface. You get a smaller sphere, one dimension down, and Pythagoras gives its radius the root of 1 minus z squared. Before I run the sweep, predict the shape. There is obviously far more sphere near the equator than near the poles, so what should this curve look like? Flat. Perfectly flat, and that is not a drawing mistake. In 3 dimensions, every height is exactly as likely as every other. Archimedes knew this. 2 effects cancel out. Going toward the pole, the slice really does get smaller, but the surface is tilting over as you go. Near the equator, it is steep, so a small step in height sweeps only a thin strip. Near the pole, it is nearly flat, and the very same step sweeps a wide strip. Slice shrinking, strip widening. In 3 dimensions, those two are exact opposites. Their product is 1, and the curve comes out flat. Which also tells you there is nothing to make use of at 3 dimensions. Nothing is bunched up anywhere. If you want structure, you have to go up and watch which of the 2 effects wins. The strip widening does not care about dimension at all. It is 1 over the root of 1 minus z squared, whatever d is. The slice does care. In d dimensions, the size of that smaller sphere scales like its radius raised to the power d minus 2. So the higher the dimension, the harder it collapses as you move away from the equator. Put the 2 together and the amount of surface at height z goes like 1 minus z squared raised to the power d minus 3 over 2. Once d is large, you can say exactly what that shape is. Raising a number just under 1 to a big power crushes it towards 0, so the only heights that survive are the ones very close to the equator. Work that through and the expression becomes the exponential of minus dz squared over 2. That is a bell curve. A Gaussian centered on 0 with standard deviation 1 over the root of d. At d equal to 128, that predicts a standard deviation of 0.0884. Measure it on our rotated vector, and you get 0.0864. And notice that no integral was worked out anywhere in that. The animation was the derivation. One condition comes with all of this. Every bit of it only shows up when d is large. Run the scheme across dimensions, and it has all but converged by 64. Below about 16, there is nothing here at all, which we already knew, because at 3 the curve came out flat. High dimension is normally the thing that ruins an algorithm. Here it is, the resource. Here are 4 more vectors with nothing in common with ours or with each other. An ordinary random direction, 2 spikes instead of 1. Completely flat, and one built on purpose to be as awkward as possible for this method. Rotate all 5. What do you expect their component histograms to look like? The same, every single time. The rotation never looks at the input, and after the rotation, the answer does not depend on the input either. Whatever vector you were handed, the spread of its components was knowable before you ever saw it, which means you can go and design the 8 levels right now, ahead of time, with no data at all. So let us actually do it. We want the 8 numbers that give the smallest squared error against that bell curve. Nothing about that problem mentions transformers or attention or 128 dimensions. It is a question about one number at a time. Given a distribution, where do you put 8 points? There is a classical answer built out of 2 observations, each obvious on its own. First, suppose somebody hands you the 8 levels. Then you immediately know which numbers go where, because every number should go to whichever level is nearest. So the boundaries between them have to sit at the midpoints. Second, suppose somebody hands you the assignment instead, meaning which numbers belong to which level. Then you immediately know where each level should sit. The single number closest in squared error to a whole collection of numbers is their average. So each level belongs at the average of everything assigned to it. Each step is exactly right given the other, and neither can make the error worse. So start anywhere at all, alternate them, and they converge. The levels bunch near 0, where most of the distribution lives, and stretch out toward the tails, where it does not. They are written in units of 1 over root d, which is the width of the distribution. Now, a table out of a textbook. The 3-bit Lloyd max levels for a Gaussian worked out in the 1960s and reprinted in every book on the subject since. It is the same table. So the codebook is not the contribution. Anybody could have looked it up. The contribution is the argument from the last scene, and what it buys you is the right to use this table on data somebody picked in order to break you. Store the vector's length as one ordinary number and divide it out so what is left is purely a direction. Rotate that direction with the one fixed matrix. Replace every component with whichever of the 8 levels is nearest, and write down that level's 3-bit index. Pack the 128 indices together, and you're finished. To decode, look each index up in the table, rotate back using the transpose of the same matrix, and multiply by the length you stored. That is TurboQuant. Now the 3 things we said we needed. One codebook, fixed offline before seeing anything. This one was fixed before the video started. Good on every vector any model produces, including the worst one you could be handed. That is what those 5 histograms were. And no per block constants. There is a single number for the entire vector, and it is its length. The encoder never looks at the vector to decide how to encode it. Same fixed rotation, same fixed table, every time. Run it on our vector. The counts are lumpy, and they should be. This is 128 numbers, not a smooth curve, and one particular draw of the rotation. But the shape is unmistakable, and it is the one the sphere predicted. That is why the table fits. One piece of bookkeeping, and it is why the honest number is not the one I opened with. The length we divided out has to be stored as one ordinary 4-byte number for the whole vector. So the real cost is 128 3-bit indices, which is 48 bytes plus 4 bytes for the length, 52 bytes, that is 3.25 bits per component rather than 3.00. It is what shipped implementations measure, and it is what this video uses from here on. The cosine between the reconstruction and the original is 0.9888, but it is a good number about one vector, and what we demanded earlier was much stronger than that. What we demanded was a codebook that works on every vector, including the worst one anybody could hand you. So let us test that by handing it 2, on the left R's, one enormous component and 127 tiny ones, about the least convenient thing you can give a quantizer. On the right, an ordinary random direction. Nothing to trip over. Same quantizer, 3 bits, both of them. First, the naive grid from the opening. Its squared error on the spiky vector is 0.0989. On the ordinary one, 0.050. About twice as bad on the awkward input, which is what you would expect from a method that fits the data. Now the same 2 vectors through TurboQuant. Predict those 2 bars before I show you which comes out worse, and by how much. 0.0330 and 0.0339. They are the same. Not close. The same, give or take which rotation you happen to draw. Notice what that does to the sentence you would normally reach for. You cannot say this method handles outliers well. It never meets one. After the rotation, there are no outliers left to handle. The error does not move. That is a real property, and it is not the same thing as the error being small. Never mind beating the naive grid. How close is this to the best that any method could possibly do? There is a floor, and nothing can get under it. With b bits per component and d components, you have 2 to the b all raised to the power d, different messages. Every direction on the sphere has to be sent to one of them. Scatter those points as cleverly as you like. There is still, somewhere, a direction that is not close to any of them. Push that through and the bound is simple. At b bits per component for any quantizer, some input has squared error of at least 4 to the minus b. At 3 bits, that is 0.0156. Averaged across vectors, we measure 0.034. We sit a factor of about 2 above the floor. What does that factor do as you spend more bits? 1.44, 1.86, 2.17, 2.39, 251. Look at the gaps. 0.42, then 0.31, then 0.22, then 0.12. The factor is not climbing forever. It is converging. On 2.7207, which is root 3 times pi over 2. That constant has a name and a date. The Panter-Dite constant, published in 1951, it has nothing to do with rotations or attention or anything else in this video. It is the price of describing the coordinates of a vector one at a time instead of the whole vector at once. Part of that price you can see. Quantizing each coordinate separately carves space into boxes, and a box has corners that sit too far from its middle. The rest comes from being forced to use the same number of levels on every coordinate. Either way, it is a fact about scalar quantization, which reframes the theorem. It does not say we got close to optimal. After the rotation, the only price you pay is the ordinary price of quantizing one number at a time. Being handed the worst possible vector costs you nothing extra. Randomness turned a worst case into an average case. Nothing about the data improved. The vector we started with is exactly as awkward as it always was. What went away is the chance that it had been picked badly because the rotation is drawn after the data is fixed, and whoever picked the data does not get to see it. So that is the method, and by the standard it was designed against, it is essentially as good as it can be. Everything in this video so far has tried to make one thing small. How far the reconstruction sits from the original. Squared error. But nobody actually wants to reconstruct a key. Attention never asks what this vector was. It asks what its dot product with my query is. Those are different jobs, and nothing we have done was aimed at the second one. So measure it directly, start at 1 bit per component where the effect is largest. If the compression were perfect, every point would land on the diagonal. They do not scatter around the diagonal. They sit on a line, and the line is not the diagonal. Its slope is less than 1, which means every dot product comes back short, every one of them in the same direction. Measured 0.6413. And the paper predicts 2 over pi, which is 0.6366. The reconstruction is systematically shorter than the original. Not rotated, not noisy. Shorter? Lloyd Max puts every level at the average of the numbers assigned to it, and that is exactly the condition that makes the error sit at a right angle to the reconstruction. So the original splits into 2 pieces at right angles, the reconstruction and the error. And Pythagoras gives you the squared length of the reconstruction as 1 minus the squared error. The squared error at 3 bits has been on screen for 2 scenes. It is 0.034, 1 minus 0.034 is 0.966. Measure the shrink at 3 bits and you get 0.9655, small enough that ignoring it is tempting. It is not noise. Noise would push some dot products up and some down, and over thousands of keys, it would average away. This pushes every single one of them the same way, every time. That is a bias. And the squared error we spent 2 scenes making small never saw it, because a systematic shrink and a random wobble of the same size look identical to squared error. The fix starts by giving something up. Take 1 bit away from the codebook. At a budget of 3, Lloyd Max now gets 2. Quantize with those, and look at what is left over. Original minus reconstruction. That is the residual. The part you failed to describe and the part responsible for the shrink. Now spend the final bit on it, but not to reconstruct it. Pick some random directions, fixed in advance, the same way the rotation was. Take the dot product of the residual with each one. Then throw away everything except the sign. 1 bit each, which way the residual leans against each direction. Plus 1 number for its length. That sounds like far too little. The stored key gets crushed down to signs. The incoming query does not. It stays in full precision. And with only one of the two sides signed, the average of that estimate comes out exactly in proportion to the true dot product. Sign both sides and you get a function of the angle between them instead. And an angle is not a dot product. The asymmetry is doing the work. And it is exactly the asymmetry a cache wants. Millions of stored keys, one live query. Compressing the query would save nothing. So does it work? Put it back on the 1-bit cloud where the defect was largest. Slope 0.6413 to 1.0003. The defect is fixed, and it is fixed exactly, which is not a word you get to use very often. Which makes what happened next quite strange. After the paper came out, 5 separate teams built this method into llama.cpp independently of one another. All 5 dropped the correction. Not because it failed. Have a guess before I tell you. What could possibly be wrong with an estimate that is exactly right on average? Same total budget, 3 bits either way. All 3 to the codebook on the left, 2 to the codebook, and 1 to the correction on the right. The right-hand cloud is centered on the diagonal. It is also much wider, about 5 times the squared error. So the correction did not remove the error. It moved it. It turned a systematic shift into random spread. 2 things go wrong at once. First, you took a bit away from the codebook, so the residual it must cope with is the one a 2-bit codebook leaves, not a 3-bit one. That is 0.116 instead of 0.034. Second, the sign trick has noise of its own. You are recovering a dot product from a pile of 1-bit votes, and that carries a factor of pi over 2. 1.571 times 0.116 over 0.034. About 5.4, which is the number on the clouds. Zero bias, 5 times the variance. That is the trade. So when is that trade a good one? Total squared error is bias squared plus variance. The variance barely depends on which pair of vectors you hand it. The bias is a percentage of the true dot product, so when that dot product is tiny, a percentage of it is tinier still. Plot both against the correlation between the query and the key, and somewhere they cross. Left of that crossing, variance is the bigger term, and you keep every bit in the codebook. Right of it, bias is the bigger term, and the correction pays for itself. At 1 bit, the correction wins as soon as the correlation passes 0.27, and most pairs manage that. At 2 bits, 0.51. At 3 bits, about 0.85, which means near duplicates and nothing else. At 4 bits, there is no crossing at all. That settles the argument, because the 2 sides were not doing the same thing. Nearest neighbor search is entirely about the largest dot products, because those are the neighbors you're looking for, and it runs at 1 or 2 bits. That is the right-hand side of the chart, and it is where the paper tests the correction. Attention at 3 or 4 bits is spread over thousands of cached keys, almost every one of them close to perpendicular to the query. That is the left-hand side. Both sides were right about their own case. One measurement is left, and it is the decisive one because attention never uses a dot product on its own. It ranks them. What matters is which keys end up with the weight. One query, 4096 cached keys, 3 bits, 300 trials, and measure what the softmax does with each variant. Read the first column on its own. Mean logit error. The correction is about 10 times better. Now read the other 2. It picks the correct top key about 60% as often, and its attention distribution is 4.6 times further from the truth. Multiplying every logit by the same number slightly less than 1 is exactly a change of temperature. And a change of temperature cannot reorder anything. Independent noise on every logit is the one thing that does reorder them. So the correction traded away the error softmax ignores and bought the error softmax is most sensitive to. One caveat. Those keys are synthetic, not taken from a running model. What holds is the comparison between the 2 variants, not the absolute hit rate. The direction, though, is the same direction 5 independent teams found before we did. So after all of that, what does it actually buy you? Back to the vector we started with, 108 numbers. 256 bytes in half precision. 52 bytes now? The ratio holds wherever you apply it. So take the block from earlier. 40 gigabytes down to 8.12, 4.92 times smaller. And now the part most write-ups leave out. Benchmarked properly inside a production serving stack, this is slower than half precision, between 10 and 68% more latency. Which is not a contradiction. It compresses storage. It does not compress computation. A GPU cannot multiply a 3-bit index by anything. So the cache has to be unpacked back to half precision before attention runs, all of it. Every token, you saved the memory, and then you added work to get it back. An 8-bit floating point format is worse at compressing, and the silicon speaks it natively. It compresses the multiplication as well, and it wins. So compression does not buy speed. It buys capacity. Capacity turns into speed in exactly one situation. When you are about to run out. If the cache does not fit, the server queues. Compressed, it fits. And the time to the first token drops from about 17 seconds to about 3.5. That is a real win, and it is a narrow one. One more boundary. At 3 bits, accuracy drops. On reasoning benchmarks by as much as 20 points. At 4 bits, it holds. So the honest operating point is 4 bits, not 3. So why does rotating a vector make it easier to compress? Not because it removes anything. It cannot. Same length, same angles, exactly the same information. What it gives you is knowledge of the components before you have seen them. That is the only situation in which a fixed code can be chosen. Every earlier method needed to look at the data first, and looking was the one thing we could not afford. Which leaves an odd situation. Not one theorem in this paper failed to reproduce. And the method still loses in production to a cruder one the hardware happens to support. The mathematics was never the problem here, and the mathematics is not the thing to take away. Take this instead. When you cannot design for the worst case, stop trying to make the worst case impossible to hand you.